Okay, so morning sessions will talk about emissions. Okay, and mostly emissions from combustion. Okay. There are other sources of emissions. Okay. So let's see. Okay, what do we know about emissions? So when we say emissions, what are we talking about? Yes. Yeah. So those are the two main ones, particularly NOx. Okay. Unburned hydrocarbons. Okay. Yeah, CO. Good. Yeah. Those are all emissions. Unwanted or unhealthy emissions. And if you talk about greenhouse gases, then you also have CO2 also, CO2, particulates, methane. Okay. They all contribute to greenhouse gases. Okay. So also sulfur dioxide, okay, like especially from coal. Coal contains a lot of sulfur. So if you want to regulate that, then you have to burn very low sulfur coal. Okay. So what happens when you have this, when you emit NOx or SOx, sulfur dioxide? Yeah. So there are reactions in the atmosphere. Okay. So which this NOx becomes nitric acid. Okay, SOx becomes sulfuric acid, I think. So anyway, so they acid rain, and of course they are, if you breathe, that is also very unhealthy. Okay. So it affects your respiratory, it leads to respiratory problems, causes more long-term damage to lungs. Okay. Asthma, for example, somebody has asthma, it can make it more severe. Okay. So here I'm just showing particulate emission. So you can see from diesel combustion. Okay. So this is all particulates coming out, okay, from the exhaust. And of course, this particulate emissions and other emissions is a severe problem in developing countries. Okay. To largest countries, it's a huge problem. And of course, this is also due to the economic development, because both these countries' economies are developing. Okay. So if you go 100 years back, US, and the Europe was in a very similar situation. Okay. Then they were less worried about emissions. Okay, more worried about the economic growth. Okay. Even like 60s, okay, in US, okay, the rivers were so polluted, okay, because there were a lot of industry, like cities like Cleveland, Chicago, Pittsburgh. These are industrial towns. Okay. The rivers were so polluted that, of course, you can't fish in those rivers. Forget about that part. The fish were dying there in those rivers. Okay. Okay. So then they had a very concerted effort, in the U.S. to move all the entire industries, steel industries, okay, other related industry out of the cities. So within like 10-15 years, they cleaned up the whole thing. Okay. So I think eventually you need some kind of a very concerted effort, okay, to take care of the emissions and environment. So this is more of a primer, so I won't go through a lot of details because we just spent 2 sessions. You can see how polluted. Okay. So this, I think, is probably typical, in the afternoon when the pollution levels are even higher, on a hot day. And same thing in peaking. Okay. In peaking, I have been there, I went there in like May. So that's like relatively cold. So you do not see this kind of okay, levels. But you see a lot of people driving those motorbikes or scooters. They are wearing a protection there. So when we also went, we bought some, what do you call those, masks, for protection. Okay, so this is just overview. So combustion generated pollutants. Okay, so climate change is driving this research to large extent. Okay, greenhouse gases. So climate change, what are the major greenhouse gases? CO2, methane, N2O, and chlorofluorocarbons. A lot of them have been banned. Okay, particulates, etc. Okay, then other emissions, unburnt hydrocarbons. So some of them are, many of them are toxins. So they are major contributor to smog. Okay, and also prolonged exposure can cause serious health issues, asthma, liver disease, lung disease, and cancer, etc. So CO can also be considered a pollutant. So it's a byproduct of incomplete combustion. You see, like if you have a rich combustion, then you have CO produced. Okay. Of course, even we are talking about the very minor concentrations of CO, which can reduce the blood's ability to carry oxygen. And we all know that overexposure is fatal. CO is very dangerous because there is no smell. Okay. And there have been a lot of cases, I mean not a lot of cases, but many cases that like people start the car, okay, the garage is closed, but that can lead to death because of CO. Because there is not enough oxygen when the garage is closed and the car is on, so that can lead to fatal to death. Okay, when we say NOx, okay, so there are two chemicals, NO and NO2. Okay. Combustion, predominantly it produces NO and it produces some NO2. Okay. And NO then also reacts to form more NO2 in the atmosphere. Okay. So both are problems in NO and NO2, and then they react with nitrogen in air in the environment. Okay. And that leads to acid rain and also smog. Okay. Like in US, LA, that was a big problem, the smog. Okay. Similarly, oxides of sulfur, okay, from fuels which contain sulfur. In addition, there are NOx and volatile organic compounds. Okay, so they react with the ultraviolet rays and form ozone. Okay, so this is also a problem in big cities in India. Okay. And so this is a bigger problem during afternoon or when sunny days. Okay. So it causes respiratory problems and other health issues such as damage to lungs, weaker immune system, chest pain, A lot of this material you can just find on the Wikipedia or online. Okay. And then of course we'll talk about soot and PM. There are a couple of slides. Okay. So what is PM, particulate matter? Okay. It's a complex mixture of solid particles and can be liquid droplets suspended in air. Okay. So from diesel combustion, it's like soot, okay, plus volatile matter. That's particulate, PM. Okay. And then it has other constituents like nitrates, sulfates, dust. Okay. So, dust also, like many countries, dust is a big problem. Okay. So, the PM may be directly emitted, okay, like from fire, particulate, the soot produced from fire, that can be a major issue if there are some big fires. Okay. There have been incidences where there was a big fire in a country and that led to more deaths during that time. Okay. And it can also form in the atmosphere from reactions of gases such as sulfur and nitride oxides. Okay, so, SOx and NOx can also contribute to PM. Then all the bad health effects, okay, exposure to particulates, okay, especially the fine particles. Okay. Fine particles, earlier the thinking was it was the 10 micron particle which were harmful, because those can be, you can breathe them in. Okay. But more research has found that it's actually the 2.5 micron, it's called PM 2.5. Those are the most, pose the greatest, health risk, because they can go deep into the lungs. Okay. So, when we say PM 10, okay, it's not just the 10 micron, anything below 10 also is included in PM 10. So, 2.5 is also included. Only thing is 2.5, the mass is very little, because mass goes as the size to the cube, right. So, so they do not have a lot of mass, but they are much greater in number. So, that causes that's a serious, more serious health risk. Okay. So, again that's a picture of the New Delhi skyline, the environment there. Okay. For particulates, okay, especially they use this air quality index. Okay. So, it measures the concentration of PM 2.5 in air. So, there is a formula where how they calculate this air quality index. So, now most of the countries they follow this index, okay, and it's reported every day. Okay. Indicator of the air quality. Okay. So, for example, in US the Environmental Protection Agency, okay, according to that, a reading between 0 and 50 is considered good. Okay. Now, in Delhi typically it's several hundred. Okay. Sometimes it may exceed even 1000, but it's like 200, 300, 400. Okay. And it's reported I'm not sure, probably every day I'm guessing. I think I have a chart here that I took from the internet. I guess this is how it is reported. This is particular location in Delhi. So, that particular day it was 177 AQI. And then PM 10, PM 2.5, okay, NO2, SO2, so they are all monitored. So, this was actually in I think yesterday or day before yesterday there was article in the newspaper. So, I just took it from there. So, contributions to this air quality index in Delhi. So, 25% from PM 2.5. So, it is not just the vehicles. Okay. Then another 25% from NOx and SOx emissions. So, 50% from not necessarily, because the PM is not just from vehicles. It is also from crop burning, burning of wood, burning of crop waste, A lot of it comes from, a lot of garbage is burnt, and of course, there are coal plants. So that's another 50%. Can ignore this part. Okay, because of the concerns, okay, due to health risks of these emissions, so there are very strict regulations. Okay, and strict means they are becoming increasingly more strict. Okay, and that shows gives the historic perspective. In the developed countries. Okay. So in US, so if you look at like 8 or 9 year period, okay, so the NOx, so this emission value is reported as grams per kilowatt hour of power. Okay. So 2.7 grams, okay, in less than 10 years by a factor of 10 reduction. Okay. And same thing goes with for PM. And in European Union they have this Euro 3, 4, 5, so increasingly stricter regulations. So 3 to again very similar to US. This maybe a little bit lagging compared to US. Like California, for example, they have like, I think they are eventually going for 0 NOx emission. Okay. But anyway, the main point is that they're becoming, so the engine manufacturers, car manufacturers, this is a continuous challenge to meet these standards. Japan, similar thing, maybe not as restrictive as US, but the PM emissions, very similar story.
Sir, in USA, whether the industries follow the norms?
Oh yeah, there are very strict regulations. Like for example, I'm not like into that topic that much, but actually it's a timely question. This this was a Paolo Berta. He was PhD student, finished around this time 2006, 2007. Now he works for I forgot the name of the company. It's a huge consulting company, and one of their big consulting work is all these manufacturing companies. They hire them to check whether they follow the emissions from their plant. Okay. So he goes to different plants, checks that, and then they gives advice how they can reduce emissions. Yeah, the Environmental Protection Agency. Okay. Yeah, of course, they have to follow strictly. Yeah, I don't know like what are the fines and all those details. But yeah, they do follow.
Most of the industry are violating the norms.
Pardon?
India, most of the industry are violating the norms.
Yeah. Yeah, if you don't enforce, then it doesn't work. Okay, for diesel combustion, so for diesel, of course, both NOx and soot are still problem. There have been major improvements in both soot and NOx emissions, but they continue to be problem because of stricter regulations. So this is a cartoon of diesel combustion. This is the well-known deck diagram. Okay, it has been referenced like thousands of times, by different people. Okay, so this is like just shows the model of diesel combustion and where the NOx and soot are produced. Okay, so this shows the spray, and then you get a rich premix flame. Okay, this rich premix flame, the equivalence ratio, in this area you get the combustion. Okay. The equivalence ratio is about 2, it could be 2, 3, 4, 2 to 5, depending on the condition. Okay. So, and then you produce lot of soot in this area. Okay. And then some of the soot gets oxidized. So, so that's the oxidation of soot. So, there is a premix combustion. So, part of the total heat release energy is released through the premix combustion, then the rest is released from the non-premix or the diffusion combustion. Okay. And this is a cartoon, so it shows the diffusion flame around the periphery, okay, or in the periphery. So, the most of the NOx is produced in this diffusion flame. Okay. So, it lists the various zones. So, diffusion flame is shown like this, okay, and this line here. What else? The rich, okay, mixture here, okay. Then you have the fuel rich premix flame, that's the blue, okay. Then you have the initial soot formation right there, okay, next to the rich premix flame. Thermal NO production. So, we will discuss in a minute, there are like 4 types of NO sources. Major generally is thermal NO. Okay. And then there is a soot oxidation. So, this is a soot oxidation zone. Okay. So, this was the motivation for our work. Okay. So, this is in one of the papers. So, instead of doing diesel combustion, okay, in a like university lab scale, we did this, we had this partially premixed flame in the experiment using counterflow configuration. Okay. And here you have the rich premix flame, and then you have the non-premix flame. Okay. And student made many different measurements, for NOx, for soot, for all many other intermediate hydrocarbon species in this flame. Now, later on 2010, I had another student, Bendu Shom. So, he actually did the diesel simulation of diesel combustion, okay. Not in a diesel engine, but there is a constant volume reactor. It's called the Sandia reactor, because there is a lot of experimental data available in the Sandia. I'll show you like 1 or 2 slides on that later on. But his contribution was, he was able to reproduce this kind of diagram for a real combustion. Okay. So, through simulations, he showed the flame is established here, and then blue is the rich premix combustion. Okay. So, he used a flame index, which can distinguish between the rich premix combustion, because this is a turbulent flame now. So, it is very difficult to identify where is the rich combustion and where is the non-premix combustion. So, he was able to do that. So, this flame index, when it is 1, it shows the non-premix zone, which is this one, and when it is 0, it shows the premix combustion. Okay. And then, of course, part of his work was to predict where the flame is located, so that they find the lift-off length for the flame. Or here the equivalence ratio is indicated 2 to 4. Now, how many are familiar with this kind of diagram? Okay. I think if you work in the diesel combustion, they are all very familiar with this diagram. So, there is a classical optimization problem that if you change conditions, so you may reduce soot, but the NOx will increase. If you do some other thing, then you can reduce NOx, but then the soot will increase. Okay. So, a lot of diesel combustion research, they try to find ways to reduce both NOx and soot. Because for both, there is still they have to do after treatment, if you want to meet the regulations. Okay. So, what is this diagram showing? Qualitatively, the temperature regime for the diesel combustion and the local equivalence ratio. So, this tells the same story. So, if you are fuel rich, equivalence ratio, you go to higher equivalence ratio, you produce more soot. Okay. And the temperature is at a lower temperature like 2000. Okay. Diesel combustion typically temperature is like 2800, 2700. Okay. Because when you inject the fuel, the mixture temperature is already like 800, 900, and then the combustion occurs after the temperature. So, the peak temperature is like 2800, 2700. So, as you go to higher temperature, but if you burn lean, then you can avoid soot by burning lean. Okay. But typically the temperatures are higher, so you produce a lot of NOx. Okay. So, amount of the NOx produced is a very strong function of temperature. Okay. So, a lot of work has been done this low temperature combustion, where you burn lean and you also reduce the temperature, by various means, by controlling the injection behavior, fuel injection, by having a lot of exhaust gas recirculation. So, from the exhaust gas in diesel engine, you clean that exhaust gas and then you inject it through with air. Okay. So, that is basically exhaust gas, means it contains CO2 and H2O, more CO2 because they remove some moisture also. Okay. So, that is used to reduce the temperatures. Okay. So, they can use excessive amount of EGR to reduce that, and then there are other, they control the when you start injecting, to achieve this low temperature combustion and reduce both NOx and soot. So, you can find a lot of papers. This diagram I taken from this paper. So, LTC is the low temperature combustion. Okay, now some details of NO production. So, this you can find in most combustion books, and there are a lot of papers. So, there are 4 major well known routes for NO production. Okay. So, when the temperatures are high like 1800, about 2000, then most of the NOx is produced through what you call the thermal NO mechanism. Okay. Thermal is called because it is very strongly dependent on temperature. Okay. So, if you can keep the temperature below 1800 in your combustor, then you can avoid the thermal NO. Okay. And in like gas turbine combustion, that is what they do. They try to burn very lean. Okay. As you make it leaner, you reduce the temperature and reduce the formation of thermal NO. So, it is directly related to the fuel oxidation, because when you have combustion, fuel oxidation, you have the radical species, right, O and OH, and the nitrogen is coming from air. So then there are reactions between OH and nitrogen which lead to NO. So this is the initiation reaction. You can say the nitrogen reacts with the O radical to produce NO, and then it produces nitrogen atom, and then N can react with O2 directly to produce more NO. So for a long time these two were considered the major reactions, which is the thermal or the Zeldovich mechanism. And this is to indicate, this is okay, because more dominant at higher temperature because the activation energy is large. So this is the reaction rate constant for the first reaction, for the forward reaction. Again, the reaction can go in both directions. Okay. Then subsequently, in addition to these two reactions, okay, people found that this reaction is also important. So it's relatively contributes less. So now all three are reported as the reactions, for responsible for thermal NO. So most of the softwares, which are like 3D softwares, generally they contain thermal mechanism, not all other mechanisms, right? Because you don't have chemistry to predict, other species which are important, for other mechanisms. But more and more you'll see that the people are, including other mechanisms in their software. The other major source is the prompt NO mechanism. Okay. This, I think the prompt word comes because this is like a slow process. Okay. This reaction occurs slowly compared to the prompt NO, if the conditions are right. So the prompt NO formation is very intimately coupled to the fuel oxidation chemistry through CH. Okay. So you have to have CH species to start the reactions for prompt NO. So that means if you have hydrogen combustion, okay, then there won't be any prompt NO. Okay, you only have the thermal NO. Because the initiation reactions, require CH. Okay. And we know, we have looked at the chemistry, like all the hydrocarbons, they produce C2H2, intermediate, species, and then from C2H2 and other species you produce CH. Okay. So CH then reacts with N2. So this is your primary initiation reaction for prompt NO. Then there are a series of number of reactions which lead to the formation of this prompt NO. Okay. So you produce HCN, okay. Then you produce, reacts with O, produce NCO. I'm showing only some of the reactions. Then NCO, okay, produce NH, produces N, then that leads to NO. So this is like one of the routes. There are 3 or 4 different routes, in this prompt mechanism. Produce this prompt NO. So this is also more relevant at fuel rich conditions. Okay. So if you have fuel lean conditions, then there is very little CH. Okay. There is still CH, but much lower value. Okay. So this is more relevant at rich conditions because you get C2H2. Okay. You can even do equilibrium calculation and see there is more, as you increase the phi value, you go rich, then you see there will be more C2H2 and CH, even for equilibrium case. Though equilibrium does not give you the complete picture, because equilibrium only gives you the final products, right? Okay. But during real combustion, there is C2H2, okay, and before it gets burned, it will produce CH. Okay. So before C2H2 is consumed, it will produce CH, and before CH is consumed, it will start producing NO. So the flame is a more dynamic system. Equilibrium only gives you the final values. But it will definitely give you qualitative behavior. Okay, so this is one of the routes. So this figure is given in Turn's book, shows different routes for the prompt NO. So we just talked about this SCN, NCO, NH, N, and then NO. But then there are some other routes. Okay. But most of these routes, start with CH. So it could be CH1, it could be sometimes CH2 and CH3 also. Okay. So hydrocarbon species. So overall, okay, if you lower the temperature, then thermal NO is significantly reduced. Okay. And if the mixture conditions are rich, okay, so if the temperature is even low, you can produce a lot of prompt NO. Okay. So these are compared to the thermal and prompt, okay, these are less important. So third one is called N2O intermediate mechanism. So this is typically more important in lean conditions, when phi is less than 0.8, and also low temperature conditions. So these are the relevant reactions. So N2, so this is like requires 3-body reaction. That means this probably becomes more important at high pressure. Okay. So N2 produces N2O, that's what's called N2O intermediate mechanism, and N2O leads to NO. Okay. Then the last one is called NNH mechanism. So this is also part of the prompt, because you see that in prompt, okay, I can't see right now, but in prompt also you produce NNH. Okay. And so basically N2 reacts with H to produce NNH, and then NNH reacts with O to produce NO. Okay. And this is related to the prompt NO mechanism. So other steps, once you have this NNH, NH, so see NH is involved here also. Okay. So once you have NH, it will follow a lot of steps which are common to this. Okay. Also, okay, NO can be converted to NO2, if you have HO2. Okay, so that will be a source of NO2. So NOx means NO and NO2. Okay. And of course, NO is then converted to nitrogen oxide in the atmosphere, and then to acid, so leading to form acid rain and smog. Any questions?
So you had low temperature conditions,
Yeah.
but NOx combustion is favored only at high temperature.
No, low means like 1700, 1600. Okay. So yeah, that's a very good question, because if you burn lean, right, lower the temperature, then you can avoid both thermal and NO. Then you have to worry about the N2O mechanism. Okay. So then these sources will become more important. In normal conditions, these are not as important. Also, most of the reaction mechanism, not most of the, lot of reaction mechanisms like GRI3, Professor, they were showing, you can download GRI3. So, and you can download a lot of other mechanisms. So, a lot of these mechanisms, they contain all these 4 routes for NO production these days. So, if you download, you can look at those reactions for NO formation. Okay. So, then I have some results in mostly in counterflow flames, but you go to the literature, you can find lot of results on this NO formation in jet flames and in real turbulent flames. Okay. So, most of the results like what we have worked on. So, this was one of the PhD thesis project 2010 to 2015 during that time. So, we were looking at 2 fuels, heptane and heptene. Okay. So, the focus was on the effect of fuel unsaturation. This you call a saturated fuel, because it has the maximum amount of atoms of hydrogen. So, when there is one double bond, you call unsaturated. So, this is heptene, and why it is called 1-heptene? Because double bond is here. If it was say somewhere here, then you call whatever 3-heptene. So, the position of the bond is also important. So, when you have this double bond, then the reactions, dominant reactions, they are different compared to this. So, we are looking at the effect of this, and this was motivated from some other due to some other factor. Like 10 years back, there was now the interest has reduced to some extent, but there was huge interest in biodiesels. So, the biodiesel components they contain both saturated and unsaturated components. And biodiesels are known to produce more NOx, less soot compared to diesel. So, that is the established fact that combustion of biodiesel in diesel engine reduces the soot, the PM significantly, but it increases the NOx. So, we were interested, why does the biodiesel increase NOx? And one of the reasons people were thinking was because of the unsaturated components. So, we did not do biodiesel that time, we did this to see the effect of unsaturation on both NOx and soot. So, one student was doing this triple flame. So, you can see this is the cartoon of this counterflow configuration. You have the fuel jet and then the air jet, they are impinging on each other. Now, to get triple flame, you have some air here and you control the equivalence ratio in this fuel jet.
Sir, both are jet containing fuel and air mixture.
Yeah, then you get triple flame. If there is no fuel here, yeah, see, starting point is this is fuel jet, this is air jet. So, then you will get a diffusion flame. Now, if you add some air to the fuel jet, then you will get a double flame. You will get a rich premix flame and a diffusion flame. So, I will show some results for that. And then if you also add some fuel, but here the mixture is lean. equivalence ratio may be like 0.4, 0.5, 0.6. Then you get a triple flame, you get a lean premix flame. Okay. So one student was simulating the triple flame, there was another student doing the double flame. So we look at the effect of fuel on saturation on NOx, pH, and soot. So first I'll show some results for the triple flame. So here, okay, the air jet is on this side, so it contains some little bit of fuel. So this is lean premix flame. Okay. So this is distance from the air nozzle. Okay. Other side is the fuel nozzle. So that contains rich mixture, so you get a rich premix flame. Okay. Then, okay, here you have, okay, the solid line, that's the stagnation plane. Okay. So going back here, so the stagnation plane is shown like by this broken line. Okay. And typically the diffusion flame is located on the oxygen side of the stagnation plane. Okay. So that is what is shown here. Actually, it's very close to the stagnation plane. Solid line is the stagnation plane. Okay, and you can see that the okay. No, actually, this is for two different fuels. So both are stagnation plane. Let me correct that. So this is for two fuels, heptane and heptene. Okay. So we are comparing the results for both. Okay. That's why there are two lines for everything. Okay. So this is the stagnation plane. Okay. Solid is got all mixed up. I don't remember which one is. Yeah, one is dash line, other one is solid. So this one is from heptene. Okay, so dash line is for heptene. Okay. Solid line is for heptane. Okay. So temperature is also a little higher for heptene. Okay. If you look at the adiabatic flame temperature from table, for heptene it will be higher compared to heptane. So this is the okay. So the main observation is this is a rich premix flame, this is a lean premix flame, and this is the diffusion flame, where the temperature is the highest. Okay. So from here to here, combustion is going on. Okay. So a lot of chemistry involved. And now the red line so red line is the temperature. Okay. So temperature is slightly higher for, look at the total NO. NO is significantly higher for heptene. Okay. So this was like an initial evidence that unsaturated fuel produce more NO.
It is common with adiabatic flame temperature getting higher for alkenes as compared to alkenes.
Yeah, not a big difference, but there is higher. Okay. But for NO there are other reasons. Okay. The chemistry is important also. Okay. So here those are the conditions. For the rich mixture, equivalence ratio was 1.5. For lean mixture on this side, it was 0.8. Okay. So overall observation is that the flame structure looks very similar for these two fuels, not a huge difference, but NO is significantly higher, okay, for heptene. Then we had all the four mechanisms for NO. Okay. So you can study the effect of each source of NO, okay, or you can analyze each source of NO. Okay. What you do is in your reaction mechanism file, only the reactions for one source, say thermal NO. Okay. So, thermal NO means you only keep these three reactions, and then you remove the other reactions and then do your calculation. Okay. Then you do for the other three same way. So, you can look at how much each is produced. Okay. Doing this, of course, you have to do many computations. So, this is what student did. So, you have the prompt NO. Okay. So, the blue line is the prompt. Okay. Thermal NO. So, look where the thermal NO is produced, in the diffusion flame. Okay. Because why in the diffusion flame? Because temperature are the highest there. Okay. Whereas the prompt NO is produced here, where you have rich combustion, mixture is fuel rich. Okay. Whereas NNH and N2O, they are more on the lean side and then also in the diffusion flame. Okay. But for us, the interesting result was there is more prompt NO and more thermal NO with heptene. So, this was using ChemCAIN. So, doing this 1D calculation advantage is you can do a lot of analysis by changing conditions. Okay. If you have to do turbulent flames, which takes like several days to compute one case, it will be very difficult to do this kind of analysis. Or if you do experiment, then also it takes a lot of time. Okay, then the software has this capability. You can look at the reaction rates. Okay, so this is the rate of production of NO. Okay, the total rate of production of NO versus X. Okay. So again, what you see is NO is produced in the rich premix zone, non-premix zone, and the rich highest in the non-premix zone. That is the rate of production, not the concentration of NO. Okay, the rate of production. And then student looked at thermal prompt N2 and NNH rate of production. So, this was a very interesting result. Okay. So, let us start with prompt. So, prompt is produced here, right, 1.6 centimeter. So, you see the rate of production of prompt. Everywhere else it is almost 0. Okay. And again, it is rate of production is higher for heptene. Okay, where is thermal NO? Around 1 centimeter, which is here. Okay. So, that is where the thermal NO is being produced. Similarly, we can look at N2O is in the lean zone at 0.5 in the lean premix flame. Rest very small contribution. Okay. Same thing, so N2O and NNH primarily in the lean premix flame. Okay. So, that was another advantage of using a triple flame, because if you just do diffusion flame, you cannot see all these effects. Okay. Okay. And then we did more analysis. Okay. So, prompt NO is related to the, and of course, this is a known fact. We already discussed. It comes from the CH. Okay. So, we plotted the C2H2 and CH in this triple flame. Okay. So, you can see that C2H2 as well as CH, most of this is produced in the rich premix zone, and that is where the prompt NO is formed. So these quantities are very small, it's like 1 ppm. Then the last part of his thesis, he did some preliminary calculations, for these three biodiesel components. Methyl deconate. This terminology comes from that there is this group, I think it's called carbonyl group, I forgot the name. So you have a C here, and then a double bond with C, then O, and there is a CH3 here. When it is blank there, it doesn't mean there is nothing there, there's CH3 there. So that's the common group that comes from when you produce this esters. So you take like any oil, and then there is a reaction with either forgot the name. What is that? Potassium, KOH or NaOH. And then from biodiesel, this part comes. So you form these various biodiesel components. Depending on the source, whether it's soybean or oil. So there are larger ones. So deconate means, so there is a carbon, that group, and then there is C10 on this side, which is very similar to hydrocarbon. So which is decane. So C10H22 combines with this to form that. This is decanote, this is decinote. So deci, so you change A to E. So decane, it becomes decene, which is one double bond. Like propane becomes propene. So same way decane will be decene. And then other part, methyl part is here. It's called methyl because there is a CH3 here. So 2D means double bond. So this is one carbon that's on the second carbon. First and the second carbon. Double bond. This is called 9D because it's on the 9th and 10th carbon, starting from this side. So this was about 4 years back. He did the work in like 2012. Paper came out in 13. So that time, the mechanisms for these biodiesel were not very well established. So that's why we call only preliminary results. So we only did very limited study on these three. So I just have two results. So this is the total NO, in one triple flame calculation. So the main observation is, that the two biodiesel with double bond, they are producing more NO compared to without the double bond. So green one is the methyl deconate, and this is decinote 2 and 9. And then this can be related to the CH. CH is also higher in the unsaturated biodiesels, so which provides another evidence for what we studied in the simpler flames with heptane and heptene. Any questions? Yeah.
Can you go back to counterflow?
Yeah, this is also counterflow.
Can you go back?
Oh, go back. Yeah, sure. Which one?
The image of flow, where the flames were. This one.
Oh, yeah. This one.
This one.
Oh, where did it go? This one? Okay.
here we are taking phi is equal to 1.2 and phi is equal to 0.85. The phi is different for the both shares. What if phi is same for both?
Yeah, that's a good question. When the phi is same for both, then you'll get two premix flames.
So the diffusion flame is still there inside the stagnation flame.
Okay. If phi is, let's say, 1.5,
Both are reached.
yeah, I think there should be a diffusion flame. We have not done that.
Let's say phi is equal to 0.8 for both the jets.
If phi is 0.8, then you'll only get two premix flames. We had done those cases. Okay.
So there will be no triple flame.
No triple flame, yeah. If you want to study just premix flame, okay, so phi 1 or less, okay, you'll get two identical premix flames. Okay. If you keep the velocities also same.
So in the stagnation flame, what will be there?
Yeah, no flame there. Yeah. Okay. Some people also study this, okay, for they get some, for turbulent flow modeling, okay, they get these flame speeds from this counterflow flame. Okay. So what they do is, because in a turbulent flame you have this flame stabilized either bluff body or swirl, okay, then the products are sustaining the flame. The products gets recirculated, okay, because there is a recirculation zone. So what they do is to model that scenario, okay. So one stream you have, hot products, okay, like CO2 and H2 at very high temperature. Other side you have the fuel air mixture. So then you can look at the effect of those on the flame speed. You can get flame speed. Okay, so there are a lot of different simulations people do depending on what they exactly looking for. Yeah, that's excellent question. Okay. So we were just near the end of the first session. So this is again showing that CH is higher, okay, with unsaturated biodiesels. Then you did one diffusion flame calculation. So there also you see that there is more NO formed in the unsaturated components. So this is just diffusion flame now. So now equal, there's just fuel, okay, in the fuel jet and just air. Okay. So you form the flame, okay, near the stagnation flame. And same thing it shows that more CH. Actually, for some reason there was more CH in the saturated one, okay. And then we realized that the reaction mechanism is not comprehensive enough or not accurate enough to do more calculations. So unless you have a good mechanism, you cannot really publish anything. You cannot get reliable results. But it was showing some good preliminary results. Now next I'll show some, so I think we'll take a break here, and then I'll show some results from the diesel combustion simulation. Okay. So these are Counterflow simple flame where you use 1D software like Chemkin. Okay. Next I'll show some NO properties, NO formation in diesel spray flames.